3D printing in construction. I mean, it sounds like something ripped straight out of a sci-fi novel, doesn't it? But
Right.
it's definitely here. And while things like 3D printed concrete have, successfully secured their place, allowing for some really incredible architectural complexity, well, that's just one piece of the construction puzzle.
Exactly. Yeah, with concrete, it's really taken hold. But when we talk about building structures, you need materials that can bear load reliably, often for like decades or even a century.
Right.
And that's where things get a bit murky for the other materials in additive manufacturing. I'm talking specifically about polymers and metals, especially when you think about using them for primary structural support elements. Construction professionals, they rightly raise an eyebrow. They ask, is this technology really robust enough? Can it handle the high demands of long-term building integrity?
Yeah, and that skepticism, it feels warranted, right? It highlights a critical knowledge gap we have.
Right.
We're trying to move 3D printing beyond just looking cool or making temporary forms into, actual components that hold up a building, even if they're just supporting joints or maybe auxiliary
The
parts.
stakes are high. They really are. And the durability of these printed plastics is a huge unknown.
A massive unknown.
And that unknown is precisely why this research we're looking at today is so foundational. Our source material, it details a study that combined intensive numerical modeling with some pretty rigorous experimental testing.
Okay.
Their goal was pretty straightforward: pin down the actual service life, and crucially, the durability of these specially shaped 3D printed specimens, ones designed for specific structural roles.
So we're diving into how they figured out how to predict failure in these complex plastic shapes.
Exactly, how they solve that problem.
Okay, let's unpack this, starting right at the foundation, like you said, with maybe the most common method for printing these polymers: fused deposition modeling, FDM.
FDM, yeah. It's really the workhorse of 3D printing for plastics. The process itself is elegantly simple. You basically melt a thin strip of plastic filament, push it through a tiny nozzle, and layer it very precisely, building the object up layer by layer until the part is complete.
That simplicity, I guess it's its major selling point, right? It means minimal material waste, you get incredible design flexibility for all sorts of complex shapes, and you can use pretty accessible, inexpensive printers. It's very democratized technology.
It is, but that simple layering process, that's also where the structural problems start to creep in. The FDM balance sheet, let's say, it has some serious liabilities, especially when we talk about components that need to bear a load over time.
Okay, so give us the rundown on those liabilities. Why can't we just, trust the filament manufacturer's data sheet? That seems like the obvious starting point.
You wish you could, but you really can't, because the finished part is structurally quite different from the raw material it started as. The disadvantages really stem from that layering. You end up with lower quality print details sometimes, large layer thicknesses compared to other methods, and crucially, these microscopic imperfections between the layers. Places where the plastic hasn't perfectly fused together. Think of it like a recipe analogy, maybe. The cookbook promises a perfect cake, but maybe your oven has hot spots or you layered the batter a bit unevenly. The final cake's strength, its structure, is totally different from just the sum of its raw ingredients.
So it's not really a solid block of plastic then. It's more like a stack of tiny, potentially fragile plastic noodles all fused together.
Yeah.
And this layering, it introduces anisotropy, right? That means the strength is completely different depending on which way you pull on it.
Precisely. Pulling parallel to the layers, along the grain, if you will, might be much easier to break than pulling perpendicular to them. And this results in potential fragility, a higher susceptibility to fracture problems, and just general instability in the material properties you actually get in the part. So the durability of the final product, especially under cycling load, it becomes completely ambiguous. You just don't know for sure.
Which explains why these components are currently sort of relegated to auxiliary roles, right? Things like spacers, maybe temporary structures, or informal joints where massive load bearing isn't the main requirement.
Exactly. But even for those secondary roles, we still need to know their absolute mechanical limits. How far can you push them?
And just to make matters even more complicated, the material properties aren't just about the plastic itself. They're influenced by a whole host of other factors.
Oh, absolutely.
With the microstructure of the print layers, how you orient the part on the print bed, internal defects you can't even see.
Even print speed and temperature settings, yeah.
It's just this enormous set of variables to try and manage.
It is. It really is. And that complexity means that relying purely on physical testing, just printing and breaking things, becomes prohibitively expensive and incredibly time-consuming. You'd have to print and break maybe thousands of prototypes to get statistical confidence.
Which is just not feasible.
Not really. And that brings us directly to the cornerstone of this research, numerical modeling.
Ah, okay, the digital sandbox. Using the finite element method, FEM. It's kind of the engineer's shortcut, in a way. It promises to be less time-demanding, certainly more economical than doing endless physical testing.
That's the dream, yes. But FEM modeling has its own big challenge, calibration. A simulation is only ever as good as the material properties you feed into it. If you just plug in the generic technical data for a standard block of that polymer...
You're ignoring all those FDM-induced flaws we just talked about.
Exactly. The layering, the orientation effects, the tiny voids, your expensive simulation ends up being inaccurate, maybe dangerously so. So the calibration process is complex. It's heavily dependent on correctly describing those properties as they actually exist in the printed part, flaws and all.
Okay, so if the usual way testing the material first, then simulating doesn't quite work because the printed material is just too inconsistent. How did these researchers bridge that gap? How did they get from the ideal computer model to the messy reality of the printed thing?
They used a really clever technique called inverse analysis.
Inverse analysis.
Yeah, it essentially flips the script. Instead of relying only on a theoretical data sheet or doing extensive material testing before simulating, they created a feedback loop between the simulation and the physical test.
Wait, hang on. So they didn't just test it once and plug numbers in. The simulation somehow informed them about what the material must actually be behaving like.
Precisely. That's the core idea. They ran an initial simulation, compared its force displacement output, basically, how much it stretched under load to the graph generated by the actual physical test of a printed sample.
Okay.
And then, iteratively, they adjusted key material parameters within the model until the simulation's output curve perfectly mirrored the experimental results. They were essentially tuning the digital material until its digital failure matched the real-world failure they observed.
That is fascinating. So they're reverse engineering the true working properties of that specific printed piece, regardless of what the original plastic datasheet might have claimed. What specific properties were they tweaking in the model?
They focused on the key parameters that dictate how a material behaves under load, primarily the elastic modulus, the Poisson's constant, and the yield strength.
Okay, let's just quickly ground those terms for anyone listening who hasn't touched the materials textbook recently. The elastic modulus is basically stiffness, right? How much force it takes before the material starts to stretch.
Yeah. Correct. It's the measure of stiffness. Higher modulus means harder to stretch than Poisson's constant. That tells us how much the material tends to squish out sideways when you pull on it lengthwise. Like when you stretch a rubber band, it gets thinner in the middle.
Right.
That thinning ratio, that's related to the Poisson's constant.
Okay, and the yield strength, that's the critical point, isn't it? Where the material stops just stretching and bouncing back. It's where deformation becomes permanent and you've essentially damaged the component.
Exactly. It's the limit of elastic behavior. So by adjusting these three parameters, stiffness, sideways squish, and the yield point, until the numerical model matched the physical test data, the inverse analysis basically proved the effectiveness of their method. It could capture the printed component's unique mechanical behavior.
And they used a reference model first, didn't they? A simpler one.
Yes, they called it Model A. It was a standard, simple geometry. They used it to validate this inverse technique before applying it to the more difficult, complex geometry.
That makes perfect sense. You've got to prove your method works on something straightforward before you can trust it on a really weird, complex shape.
Okay, so now let's talk about the physical setup for the actual experiments. How did they test these things?
The physical tests were fairly standard in principle. They involved clamping the printed samples into the jaws of an electromechanical testing machine, an FP10 model. Then the machine pulled the jaws apart at a very slow, controlled speed, just 1 millimeter per minute.
Slow and steady.
Very. And all the samples were printed with specific, consistent FDM settings. They mentioned using layer sizes of 0.2 by 0.4 millimeters.
Okay, and they looked at two distinct geometries, you said. Model A, the standard one, that was long and thin, designed mostly for simple tensile stress, pulling it straight apart.
Correct. 180 millimeters long, 20 wide, 4 thick. Tested primarily for normal tensile stress. And importantly, they ran 5 separate experiments on this Model A.
And why 5? Just for repeatability.
Exactly. To ensure the results were consistent and not just a one-off fluke. And those 5 results were vital. The graphical comparison showed excellent agreement. The force displacement curves lined up really well between the physical test data and the numerical model that had been tuned using that inverse analysis.
So that was a validation step. Proof that the calibration method worked, not just in theory, but for actual printed standard shapes.
Precisely. It gave them confidence.
But the real test, the one that kind of makes or breaks the research usefulness, that came with Model B, the specially shaped specimen. This one was thicker, structurally more complex. What was unique about its geometry? Why design it that way?
This complex piece, 170 millimeters long, 20 wide, but 11.6 millimeters thick, it was created specifically to challenge the material in a different way. It was designed to induce localized areas of shear stress rather than just that simple uniform tension we saw in Model A.
Shear, so like a twisting or sliding stress.
Exactly, which is often much more damaging to layered FDM elastics than simple pulling. Those layer interfaces are particularly weak under shear. And because it was such a complex, part-time consuming, and costly to print and prepare, they focused their efforts and ran only one physical experiment on this specific Model B geometry.
Okay, so we have this complex, shear-inducing plastic piece being pulled apart slowly, and only one physical test data point to compare against. How successful was the numerical model, the one calibrated using inverse analysis, at predicting that failure?
The success was actually quite remarkable. Not only were the overall curve shapes and the maximum load values very similar between the single experiment and the calibrated simulation.
Which is already good.
Right. But even more crucially, the numerical model accurately predicted the physical mode of failure, where and how it broke.
That's the critical part, isn't it? Predicting where it's going to break under load.
It absolutely is. The post-test photograph clearly showed the sample physically separated right at the junction where the inner and outer structures of the complex geometry met. And the numerical model had predicted that exact failure point. It did this by identifying the location of the maximum or critical equivalent plastic strain.
Okay, critical equivalent plastic strain. That sounds like some serious engineering jargon. Can you break that down a bit? What is that in practical terms?
Think of it as the point within the material where it has deformed permanently. It's gone past its yield strength, and it has essentially run out of capacity to absorb any more stretching or deformation without actually fracturing. The simulation pinpointed exactly where that breaking bubble, if you like, would form first under the increasing load, and the physical test confirmed that prediction perfectly.
Wow.
So this means the inverse analysis calibration method is robust. It's robust enough to predict these complex failure modes, even in optimized, structurally challenging geometries designed to induce shear.
This is where it gets really interesting for the construction industry, though, I think. Because knowing the single breaking point is one thing, but structural engineering is so much about durability over time, right, under repetitive stress. So they shifted focus then to determining the service life using what they called simplified fatigue analysis.
Yes, exactly. Knowing the ultimate strength is useful, but fatigue failure under repeated loading, even if the load is below the ultimate strength, is often the real killer in structural applications. So they evaluated critical points for fatigue failure. They did this by setting up a cyclic loading regime in the simulation.
Okay, what did that involve?
They essentially simulated pushing and relaxing the load repeatedly. Specifically, they pushed the load up to a stress level where the sample had already begun to plasticize slightly, where it was already a little bit damaged from the initial pull.
So testing its resilience after initial yielding.
Right. And then they compared the number of cycles the simulation predicted it could withstand at that stress level against the established SN curve for the base material, which was polycarbonate in this case.
The SN curve.
Yeah.
What is that exactly for people who might not know?
Think of it as the material's sort of death clock under repeated stress. SN stands for stress versus number of cycles to failure. It's a standard graph, usually derived from lots of experiments, that shows how many times you can stress a material, that's N, the number of cycles, before it fails, given a certain level of applied stress, that's S.
Okay, so high stress means fewer cycles.
Exactly. If you apply a high stress, the number of cycles it lasts, N, is low. If you apply a much lower stress, it can potentially last for millions of cycles. They use this established curve for polycarbonate to predict the lifetime of their specific printed part based on the peak stresses the simulation showed occurring during the cycles.
And based on their analysis of the simulation, where did they find the highest vulnerability? Where were the stresses concentrating under that cyclic load?
Well, interestingly, the stress concentrators, the points of highest critical stress under cyclic loading, were found right at that same edge level, where the inner and outer structures of the special geometry met.
The same place it broke in the single pull test.
The very same place. This confirms that even under cyclic loading, the failure is fundamentally governed by the geometry. The shape itself created a weak point. And the inverse analysis method, combined with the fatigue analysis, successfully flagged that critical location again.
Okay, this all boils down then to one really specific, potentially quite impactful number. Under that specified cyclic load condition, the one designed to test the component's limits, after yielding what was the minimum predicted lifetime they found for that specially shaped sample.
The minimum predicted lifetime of the specially shaped sample model B under those conditions was 41 cycles.
41. Just 41 cycles. That is, well, it's a highly specific number. And frankly, it sounds quite low, but it's precisely the kind of crucial hard data that's needed, isn't it, to move this technology forward responsibly.
It is the ultimate reality check in many ways. The conclusion here is absolutely vital for designers thinking about using these materials. First, the geometry of the specimen is demonstrably the defining factor in its fatigue resistance. Optimization isn't just nice to have, it's non-negotiable.
Right.
And second, this combined approach taking experimental results, using inverse analysis to calibrate a numerical model, and then running fatigue simulations, it's a proven, validated methodology. It works for accurately predicting service life and, just as importantly, highlighting the critical weak points where a design needs improvement.
So wrapping this up, what does this all mean for us or for you listening? We've seen that inverse analysis can successfully calibrate these numerical models. It makes them reliable tools for understanding the really complex mechanical behavior of FDM 3D printed parts. It's potentially a valuable shortcut to engineering confidence, saving time and money compared to endless physical prototypes.
And that confidence, it raises a really important, maybe provocative question for you, the designer or engineer, particularly thinking about construction applications. We know that these 3D printed plastic components are often talked about for use in, say, temporary structures or as auxiliary elements, not the main load-bearing parts. Now we have data showing minimum lifetime predictions that can be as low as, well, 41 cycles under specific challenging cyclic loading conditions. So the question becomes, if potential durability under load can be measured in just dozens of cycles, what level of safety factor do you need? Or how many design iterations are truly required to confidently move these auxiliary elements into more reliable, maybe even longer-term applications in construction?
Yeah.
If a component might only last 41 cycles under a certain plausible load scenario, what is the practical definition of temporary when durability can be measured so precisely and sometimes so alarmingly low?
That is an excellent thought to chew on. Our real challenge. Whether you're optimizing a simple bracket or a complex joint, understanding how that geometry dictates the component's potential depth by 1,000 cycles, perhaps just 41, seems absolutely key. Thank you for taking this deep dive with us today.